Code generation is rapidly advancing, but competitive programming, that is a totally different beast. It demands strict, flawless logical reasoning under extreme constraints. Welcome to this explainer. Today, we are looking at a foundational new paper from the DeepReinforce team detailing GrandCode, an AI system that just fundamentally altered the landscape of algorithmic problem solving.
To really grasp the scale of this breakthrough, you have to look at the previous high-water mark. Before this paper dropped, the best competitive programming result by an AI was Google's Gemini 3 DeepThink. According to the authors in the paper's abstract, that model attained 8th place. However, there is a major caveat you need to know. That finish was on historical problems. It was not tested under unpredictable, live competition conditions.
Now look at the verified payoff for GrandCode. First place, the abstract explicitly confirms it did not just win some offline test. GrandCode placed first in live, real-time Codeforces competitions, beating highly ranked human Grandmasters outright.
Section 1. AI's Final Human Stronghold. So, why is this specific environment so difficult to crack? The introduction of the paper explains that standard single-pass models fail simply because competitive programming requires strict logic under immense time pressure. The old way of evaluating AI relied heavily on static, past datasets. In those offline scenarios, an AI could easily just retrieve memorized patterns from its training data. Live contest conditions are completely different. They force the system to succeed under strict time limits and pass entirely hidden adversarial test cases right on the fly.
The authors state the stakes perfectly in the introduction, writing, "Competitive programming remains one of the last few human strongholds in coding against AI. It pushes system capabilities right up against the absolute limit of human intellect."
Section 2. The multi-agent breakthrough.
To conquer this, the DeepReinforce team had to completely abandon single-pass generation. Instead, they built a highly orchestrated multi-agent reinforcement learning system. Figure 2 in the paper maps out this entire pipeline. It essentially bridges two distinct phases. On the left side, post-training utilizes powerful foundation models like QN 3.527b. That base capability then feeds directly into the live test-time adaptation loop on the right, which iteratively improves candidate solutions through constant verification feedback.
Section 3. Inside the agentic loop.
Section 3 of the paper breaks this complex system down into 4 distinct modules. First up is the hypothesis model, which proposes structural conjectures. Second is the main solver, responsible for actually generating the reasoning in code. Third, we have a summarization model. This compresses long reasoning traces so the system doesn't exceed its context limits on those really hard, drawn-out problems. Finally, the test case generator constructs adversarial stress cases to break bad code before it gets submitted.
Figure 3 maps out the critical, very first step, which is hypothesis generation. Before it commits to writing a massive, complex solution, the agent proposes a hypothesis. It generates small, random instances and uses a brute force solver to check the underlying math. If there is a mismatch, the system forces a revision. Only mathematically validated hypotheses get promoted to the actual code synthesis phase.
The performance gains from this specific module are mapped out clearly in Table 2. The base QN 3.527b model had a pass-at-1 rate of 34% for hypothesis generation. After applying supervised fine-tuning and reinforcement learning, that pass-at-1 rate jumps up to 52%. The system becomes demonstrably better at mathematically sound conjecture.
Coordinating all these multi-turn agents creates a major technical headache known as off-policy drift. This happens because of delayed rewards. To solve this exact issue, Section 4 introduces what they call agentic GRPO. This is a variant of group relative policy optimization. It effectively combines immediate reward updates for early steps with a delayed correction mechanism, keeping that entire iterative loop perfectly stable.
Section 4. The Grandmaster payoff.
Looking at the live competitions from late March 2026, Section 2.2 of the paper lays out the exact scoring metrics. They track S-separate, which represents the score if submissions are made independently, and S-joint, which is the score when operating under a single account. For Codeforces Round 1088 specifically, GrandCode achieved an S-separate score of 16,511. Under the strict single-account limits, the S-joint score was 15,008. That joint score is naturally lower due to single-account wait times, but the performance remains undeniably dominant.
Figure 1 visually confirms the standings for those 3 live contests. Operating quietly under contestant IDs like Yoke-Co in round 1088 and Vortex-1 in round 1089, GrandCode consistently ranked first. The model systematically dismantled the problem sets faster and far more accurately than the best human minds logged into the platform at that time.
Which leaves us with a profound question about future implications. To be clear, this next part is pure speculation. If agentic reinforcement learning can push past human limits in such a highly constrained live environment, what actually happens when AI completely masters complex algorithmic logic in real time, adapting its own code right on the fly? It is a possibility that redefines the very nature of software engineering moving forward. Thanks for joining me on this explainer.